First of all, thank you very much for the invitation, and I'm very happy to be here to see you all, and yeah, in this like a very difficult situation. And especially thank you very much to Ashay for the invitation. And I first apologize, there will be many overlaps with the former lecture by Francesca, because this Euler system method will have many common features. So you will see that. So my goal is the following. So the goal of this lecture series is the first, I'd like to illustrate the how Euler system the Kato's Euler system work and are constructive. This is the first goal. Then the word illustrate means like it's not very rigorous. And the second is I think this is in some sense more important. See, by giving this lecture series, I want to kind of help you to read Kato's paper. Yes, yeah, help you a little bit to read the Kato's asterisk. The 2004 paper. Yes, this is my goal, and especially I want to share my experience to study this paper if possible, and also my focus will be on the arithmetic elliptic curves. Which means I would not deal with general modular forms. Not general modular forms. And let me start with the kind of example. So first question is how to understand the rational points on elliptic curves. Let me bring two examples. The first elliptic curve has the following defining equation: y squared equals x cubed minus x. And second elliptic curve is very similar, has the very similar equation: y squared plus y equals x cubed minus x. Then it turns out that the first elliptic curve has the following structure. Its rational points is isomorphic to z mod 2z times z mod 2z. And the second one, its behavior is very different. So E of Q is indeed infinite. So it's isomorphic to Z. And in fact, the first one is following the LMFDB table is the 32.83. And this one is 37.81. And what I want to say is that their equations looks very similar, but their behaviors are very different. So basically, we do not know the rational points on elliptic curves by just looking at the curve. So what I want to emphasize here is that we do not know whether for a given elliptic curve, its rational points are infinite or not. But as you've seen, like an L function knows. So here's the one equality here. So the human being, I mean, like L function is in some sense better than human being, something like that. This is one important inequality. And let me recall the basic facts of the elliptic curves. And I think first 10 minutes will overlap with Francisca's talk a lot. So let me recall the modularity theorem. So Wiles and Taylor Wiles. The Broy, Conrad, Diamond, Taylor. And how's the correspondence is made. So first, I consider like a Q isogeny classes of rational elliptic curves. Of conductor N. It corresponds to weight 2 cuspidal new forms with rational Fourier coefficient of level gamma naught N. And for a given like a elliptic curve, let me write the corresponding modular form is f of e, f sub e, then of course their L function coincide. Is defined by the L function sum of the an over n to the s, and real part of s is larger than or equal to 3 over 2. And of course, this an comes from the Fourier coefficient of fe. So where f of e is sum of an qn and runs over all the positive integers. Okay. Then the Birch and Swinnerton-Dyer conjecture is as follows. So E over Q is the rational elliptic curve. And the first statement, as Francesca said, is rank is same as the vanishing order of the L function, which I call it just R. And the second one is if one holds and the Tate-Shafrovich group is finite, then the formula holds. So yeah, just the limit s goes to 1 and the L E over S S over S minus 1 to the R times the Néron period and the regulator is same as the size of the Tate-Shafrovich group and the product of all Tamagawa factors. I just denote it like this. The Tam E, and the size of the global torsion squared here, yeah, where the Tamagawa, the product of all Tamagawa factor is nothing but the product of all bad primes over and the index E of QL and E sub not QL, which is the pre-image of non-singular points. Okay. And so, okay, so with the Beilinson Kato elements, what can we observe is the following. So let me move to the setting for Kato's elements, Beilinson Kato elements. So Beilinson Kato zeta elements. Okay, let me fix a prime P. Including 2. And E is an elliptic curve over Q, but I want to emphasize without CM. And T is a Tate module of the elliptic curve, which is defined by the inverse limit of the P power torsion. And V is rationalized T, which means like a T tensor QP, which is two-dimensional QP vector space. And of course, the absolute Galois group acts on V via law. So G sub Q is the absolute Galois group. And indeed, it factors through is a small extension. So Q sigma is maximal extension unramified outside a set of prime sigma, which contains P and infinity and all bad primes. It's a finite set. And why do I say this is when I say global Galois cohomology, indeed, it's Galois cohomology over of this Galois group. This is, so when I, okay, let me just write like this. So when I say this means this always. Of course, we can change a sigma. For example, we can enlarge sigma when we want, but like always there will be some sigma. And this global Galois cohomology contains the information of the rational points of elliptic curves via Kummer map. So contains the information of the model wave group via Kummer map. So we now have some method like put geometry into cohomology, especially EQ tensor QP maps to H1QV is then the geometry goes to cohomology. And after having this, then we can apply the various tools for Galois cohomology. And I want to say more on the local nature at P. So how about the QP point? One exercise is the local Galois cohomology. QPV is two-dimensional QP vector space. And the hint is to use local Euler characteristic from LAR. Okay, then we can like put the local points in the local Galois corners again. And one good thing here is that we know the dimension. Oh, sorry, one. QPV, and this is one-dimensional, and this is two-dimensional. Okay, and now we'd like to introduce some pairing. First, for the elliptic curves, we have wave pairing. So like a V cross V to QP1. One means like Tate twist. Yes, P is fixed, but it can be any prime now. And when we really like do some explicit computation, we will assume P is an odd, or even like a P is not 2 or 3, but right now P can be any prime. So this wave pairing induces a non-degenerate cup product pairing. Namely like a local Tate pairing indeed. So from the local Galois cohomology times local. Yes, so this is the, yes, is the QP is just the trivial Galois module. This is the Tate twist. Yes, thank you. H1 QPV goes to H2 QP and QP1, which is isomorphic to QP. And this is cup product indeed. And under this pairing, and the model wave part, the local model wave part is orthogonal to each other. This follows from the local Tate duality. And now we have the following commutative diagram. So let me just recall the first pairing here. And this guy contains the local model wave group. And here I just write down QP, but okay, let me just write down like this. And I regard this guy as a tangent space of the E over QP. So space of E over QP. And it contains, of course, PZP. And from PZP, we have the exponential map to the elliptic curves in the formal group level. So if I put A here, then I have the, let me say, the exponential map of the formal group of A indeed lies in here. And we're just extending this map linearly, then we have the map, and this is called the exponential map just. This is isomorphism. In the other side, the corresponding map is called a dual exponential map. We have this. So this guy indeed will be the cotangent space. So more precisely, this QP can be regarded as the global differential space. And more precisely, more explicitly, it can be just the QP, one-dimensional QP vector space generated by the invariant differential. And this guy, yeah. And this pairing is nothing but the A, B goes to A times B, and this is just the identity map, and all this diagram commutes. This is just multiplication. And also, in this setting, the kernel of dual exponential map is indeed exactly the local model Bay group, which is submodule, sub-vector space of the local Galois cohomology. Okay, in this setting, so it's a very like a small part of Kato's theorem. Kato. Yeah, this is a kind of only small use of Kato's order system, as I said. So first, I think this Kato's order system work is, I think it's announced already early 90s, but published in 2004. Okay, if, I mean, like there exists a global Galois cohomology class here, such that in the following map, so H, the global Galois cohomology to local Galois cohomology, natural restriction map, log P, and taking dual exponential map, then we have QP times omega E. Then the image of ZQ is nothing but the L value. Okay, this is the, sorry, could you please explain? Okay, there are many questions. I think right now we don't have to assume P is a good prime right now, but yeah. Also, yes, this dual exponential map is a kind of the bottom version of Perron-Liu's dual exponential map. So Perron-Liu dual exponential map interpolate this dual exponential. And okay, what's the point? So from tangent space to cohomology group, explain the map. So I regard this QP is just the, I mean, rather than saying like this PZP is regarded as the formal typic group. And then it goes to the formal group part of the elliptic curves, and by inverting P extend to the whole part, QP and the EQP tensor QP. Okay, right. Okay, now. Okay. Kato, anyway, Kato construct this ZQ, then with this element, what can we do is first corollary. Kato. Of course, the Kolibagin did the same theorem with Higgs points as Francisco explained. So the first consequence is following. So rank is positive, then L value vanishes. If you consider contrapositive, the L value is non-zero, then the rank is 0. Yeah. Okay, with this element, we can prove this. So since I assume the rank is positive and there exists a point of infinite order, let me call it P, be a point of infinite order. And under the localization map in the model vague group level, so under EQ tensor QP to EQP tensor QP, then its image generate this guy. So the image of P generates EQP tensor QP. And this piece comes from the global, and this ZQ is also global. Then using the Artin reciprocity law, like a sum of the all local pairing will be 0. So let me just write down what I just said. QV and P is a global point of infinite order, are global. So the Artin reciprocity law says it's a sum of all local pairing, including infinity. So local is 0. And also, we have if L is not equal to P, then all local Galois homers vanishes. So which using these two equality, then we also have the pairing at P is also 0. So and indeed, like this P is this P comes from the global point. So this guy lies in QP, EQP tensor QP, and the self-orthogonality of this guy. What we have is localization of this global Galois converged classes also lies in here. But this guy is the kernel of the Doric exponential. So this is 0, which means the L value at 1 is 0. This proves. Of course, so what I want to emphasize is that I only used in the bottom class of Kato's Euler system. So this is the very starting point. Of Kato's Euler system. And of course, this ZQ is a part of a bigger thing. And okay, and now recall the Selma groups a little bit. Recall Selma groups. of p power torsion point of elliptic curve, which is nothing but all the union of the pnth power and runs over from all positive integers. And the Selma group here is defined as follows. So first, the finite, Pn torsion is the kernel of H1, is the global Galois cohomology class. So like this. So which means Galois cohomology of the Galois group of Q sigma over Q. And here prime runs over all the primes in sigma. Then it factors, it factors through this quotient by local model V, Z mod P to the NZ. Okay. And by taking direct limit, we have the Selma group of all p power torsion points. And this fits into an exact sequence. EQ, E of Q tensor QP mod ZP goes to this Selma and goes to the p part of T-Shafarevich group. And of course, Q can be replaced by any finite extension or even algebraic extensions of Q. And now I can state the strengthening of Kato's theorem I said. Of course, again, like a Kolibagin also got the similar result using Higino points. Okay, so E over Q, it has no CM, so without CM elliptic curve, and P is any prime. And the first statement is if the L value doesn't vanish, then not just the model V, but like a Selma group is finite. So not only the rational points, but also the P part of T-Shafarevich group is also finite. And second, some twist is allowed. So let F over Q be a finite abelian extension. And chi is a character of Galois group of F over Q. Let's see, a character. And if the twisted L value is not 0, then the chi isotypic part of F rational points, which means like a EF naturally allows the Galois action of the action of Galois group of F over Q. So we just consider is the chi eigen part. So the group ring, but factor through chi, and Z chi is the Z as joining values of chi. In the same manner, the T-Shafarevich group of E over F is P part and its chi component, both are finite. And this theorem needs more than, oh, sorry, are you assuming bottom class? Yes. So the non-vanishing of L values corresponding to the implies the bottom class of Euler system is non-zero. Yeah. So this theorem needs more than one element ZQ. Now the theory of Euler system comes in. So what I meant is I usually regard Euler systems as a cohomological shape of L functions. And because of the following two properties. The first, I mean, the Euler systems are like a families of Galois cohomology classes. And let me just write down Z Q of as joining zeta MPN over, so I mean how can I say that? By Kronecker-Weber, all abelian extensions can be regarded as the cyclotomic extension. So I just say the abelian extensions of Q with norm compatibility. And this norm compatibility remembers all Euler factors of L functions. So it seems reasonable to add word Euler here. And I mean, this is kind of definition of Euler system. And it also has the property it recover L values, which is so-called the explicit reciprocity law. Which is a very deep theorem. Okay. So from now on, I need to explain a bit of Iwasawa theory indeed. Oh, need a little bit of Iwasawa theory. Yeah. Because we will see the L value is non-zero, then not just the P part, the whole Tate-Shafarevich group is finite. Then we need to cover some of the cover some non-trivial primes, and for this we need a bit Iwasawa theory. Anyway, the motto is the following. So a counterintuitive principle of Iwasawa theory is, in some sense, infinite extension are easier than finite extension. Finite extensions. This is just one thing in my mind. And now we will deform the Birch and Swinnerton-Dyer conjecture along the cyclotomic extensions. That is nothing but the Iwasawa main conjecture. Okay, so now I assume E is the E has the good ordinary reduction at P. And now P is odd, and P good means like P does not divide the conductor, and also it does not divide the pith-free coefficient, which means ordinary. Then consider the cyclotomic ZP extension. Its scalar group is isomorphic to attribute group of the periodic integer, and the nth layer is its scalar group is a cyclic group of order p to the n, and lambda, called the Iwasawa algebra, is the completive group ring, right, like this. So which completely means like I take the inverse limit of ZP of Galois group of each finite layer, which is isomorphic to one variable power series over periodic integer. And by choosing an topological generator of this ZP and gamma to 1 plus t gives this isomorphism. And if so let me say M is a finitely generated torsion lambda module, then M is pseudo-isomorphic to the following the modules Fi and Fi. These are elements in lambda. And pseudo-isomorphic means like there exists a map from M to here, but the kernels and co-kernels are finite. So kernel, co-kernel are finite. In this situation, the characteristic ideal of M over lambda is nothing but the product of all these Fi. Right. Okay. And another object, so-called the periodic L function, is, so let me say LPE lambda, so-called the periodic L function, which remembers all twisted L values. LE chi1, and where, how can I say that? Where let me just write down some interpolation formula. So if I evaluate the periodic L function as a character of the cyclotomic GP extension, then it is some explicit constant, up to some explicit constant, is the Gauss sum tau of E chi bar times E chi 1 and E plus, where chi is nothing but the character from the GP extension to C infinity, finite order. Okay. In this situation, the theorem of Bloch is the periodic L function is non-zero. And the conjecture, so-called Iwasawa main conjecture, is the characteristic ideal of the Selma group is nothing but the ideal generated by the PRDL function. This Q infinity and E P infinity, and taking the Pontryagin dual. And I tacitly already assume because this is finitely generated torsion module, and answer is yes. And what Kato proved is the following. So if the image of Galois representation contains a conjugate, of SL to ZP, then the one inclusion holds. So from this equality, this inclusion holds. So in my mind, this gives an upper bound of Selma groups. Okay, and using this, what we can really prove is the following theorem. So E over Q is non-CM elliptic curve, and the L value doesn't vanish. Then for almost all means over finitely many here, for almost all prime, we have the size of the Taysha for each group is P part. Divide the L values, divide by the period. So, I mean, this automatically implies that if L values doesn't vanish, then the whole Taysha for each group is finite. So, sketch of proof. As Francis already used, so not non-CM, then the Serre's open image theorem is the residual representation is surjective for all sufficiently large prime. So this implies the rho contains the image of law, image of law contains SL to ZP. So now we will remove some finitely many primes. So, okay, we first ignore all bad reduction primes. Second, and all primes dividing all vectors at S equals 1 at bad reduction primes. And third, okay, I just remove P equals 2. And I also, how can I say this? Some primes dividing certain a constant CE, which is independent of P. such that the dual exponential localization of ZQ is some factor times L value. And also removed all the primes dividing. So Q is also prime dividing the conductor, and EQ, the local points, is torsion, is size, is size, yes. Okay. And all these like dirty primes, if you remove them all, then we are fine. Yeah. And another one issue is a non-anomalous, anomalous good prime, good ordinary prime. And this part can be like removed by using the contour theorem. So, okay, so combining in Kato's theorem on the Iwasawa main conjecture plus like a non-zero finite lambda submodule type result. Due to Greenberg. And plus contour theorem due to Major. And combining them all, then we get the result. So the corollary is the elliptic curve without CM, then L value doesn't vanish, then the Tay-Shafrovich group is finite, not just the 1p part. And another remark regarding the twisted L value result. So Kato's theorem, the second one, is also very interesting due to the following corollary. The elliptic curve over Q is non-CM. Then, surprisingly, if I consider Q infinity point, which is an infinite extension, but it is still finitely generated. Of course, using Modularity Theorem, if you consider like a finite extension, then it's finitely generated. But like even putting an infinite extension, we still have the finite generated like a billion group. So how I regard this theorem is okay. Here I consider tower of fields, so Qn and goes to Q infinity. And here I put EQ infinity and EQn and EQ. Of course, I just write down this tower. And if I regard this guy as a function like this, then what's the property of this function is this function does not grow too much. I think that this type of results really shows the philosophy of Iwasawa theory very well. Okay, and let me go back to the Iwasawa main conjecture. Yes. I mean, yeah, but this explanation is very informal one. It's not like a very precise one. I just regard as naively, and it just shows like it doesn't grow too much. That's the kind of Iwasawa theory shows you. Yeah. And even like when you consider like a rational points of elliptic curves, if you want to regard it as very like a concrete mathematics, you need a group scheme, right? Yeah. Okay, back to the Iwasawa main conjecture. And of course, the one remark is the Skinner-Urban theorem is very using the Eisenstein congruence method. It's kind of the opposite way. I mean, it's the kind of opposite way to obtain the results of the Iwasawa main conjecture. Is if there exists L exactly dividing N, and the residual representation is ramified at L, then in the opposite inclusion holds. And so in some sense, this guy gives us the lower bound of Selma groups. Okay, then we just talked about the Iwasawa main conjecture. Then we can ask where this Kato-Zoro system appears in the main conjecture. So where does Kato's Euler system appear in Kato's theorem on Iwasawa main conjecture? Then this involves so-called the Kato's Iwasawa main conjecture without periodic functions. So, okay, let me consider the following elements. So if I now assume like the Kato's, so like a ZQ, any abelian extension exists. Yeah, and I will use that, especially in the p power direction. So when I say like a ZQ infinity is the inverse limit of ZQn, and this inverse limit with respect to co-restriction map lies in the Iwasawa cohomology, which is in the same manner. This is the inverse limit with respect to co-restriction map. And this limit is okay. This is a part of the Euler system relation, Euler system norm relation. And in Kato's main conjecture, this element itself plays the role of the periodic functions. And more precisely, and there exists a map, so-called the Kolman map. It's the call from the local Iwasawa cohomology to lambda Iwasawa algebra, and like local this localization of this the Euler system at like Q infinity, it maps to PIDL function. Of course, if we do not assume like a good ordinary reduction, then this ring will be bigger. And although I do not like state the Kato's IMC explicitly, but it will come later in this lecture series, is the without PIDL function and just usual PIDL function with LP using comma map. And one good thing of Kato's Euler system, Kato's Iwasawa main conjecture is the no restriction on the reduction type. So no reduction type assumption. And we will see this later. Okay. How much time do I have? Okay, 27 minutes. Okay. Yeah. So, okay, let me give some remarks on the Euler system argument. Yeah. Indeed, this feature is very well explained in the Francesca's talk. So I will draw the similar picture here. And in the Euler system argument, okay, we need a derivative process, the Kohlbergian derivative. And indeed, like we can organize these common classes more. More means like when Francesca said like some rigidity, and that's the rigid property means this word more here. And we get the theory of Kohlbergian systems. Due to Major and Lubin, and now the theory of Kohlbergian system is like extended a lot. Sorry, you were mentioning OCM specific not taking. Yes, so in Kato's Euler system argument, yes, big image. So in Kato's Euler system argument, we need some specific element in the image of Gauss representation, and it forces it like exclude the CM case. So, okay, we will like draw the similar picture, but what I want to emphasize is the Kohlbergian systems has more advantage than just the usual Euler systems. That's the so by developing the theory of Kohlbergian systems, there are two advantages. So first one is that we have a criterion to have equality. So, and the second not only just the upper bound, sometimes we are allowed to have the structure theorem. So in the Hegel, I think this kind of structure theorem is first considered by Kolyvagin in the Hegel point setting. So okay, let's see now. This Kolyvagin's 1991 Annalen paper is the very starting point, I guess, in the Hegel point setting, not Kato's of course. Okay, let me draw the picture. I usually called it Major's diagram because I saw it in Major's lecture, this big picture. Yeah, I will draw the same picture. So L values, and here's the arithmetic. Which means like a Selma groups, class groups, all the important things. And making this connection is very difficult. It's just the class number formula and Birch and Swinnerton-Dyer conjecture and Bloch-Kato conjecture. And this side, so-called the Euler system, will appear. And it's also, following the Major's words, it's algebraic treasures. Nothing but the Euler system. And this connection, is given by explicit reciprocity law in my case. And of course, the Gross-Jaget type conjecture, formula, sorry. Gross-Jaget formula. And we have some derivative process. And we get the Kolyvagin systems. And control it by global duality. Okay, this is exactly the same picture the Francesca drew. And what I want to ask is okay, in this beautiful picture, why we can't get the equality? Why we only get the like a one divisibility or one inclusion? Yeah, the reason is this derivative process. So from the Euler system, we get the Kolyvagin systems, but we do not know whether this map is surjective or not. So this is the question. And this surjectivity is exactly the criterion to have equality. This is the one connection. Okay. Okay, so now the question reduced to, okay, so what I've explained is that if I have an Euler system, we can do this. And the question is then where do Euler systems come from? Reduces to where do Euler systems come from? Yeah, this is in the theory of Euler system, the most difficult question in it. So yeah, cyclotomic units. the classical main conjecture, and the elliptic units for CM elliptic curve, and Kurzweil's theory, and Beilinson Kato elements, which is the main topic is this lecture series, my lecture series, and the Francesca's lecture series corresponding to Huygens points, or if you want to consider a higher rate modular form, then you may need to consider Huygens cycles, and now like a Beilinson flock, blah blah blah, and nowadays like the David Leffler and Serge Zerbes like launched a program to construct a various Euler system in like a various automorphic representations. And of course, my lecture series, like this guy comes from the Ziegel unit. And now let me briefly draw the very rough picture how to get the Kato's Euler system. So very, very rough picture. And this is like, yeah, it can be regarded as a guideline to read the paper, read Kato's paper. Okay, let me be honest more. It's like, so when I first read this paper, I got confused a lot because I first saw the following element is a C, D, Z, M, F, R, R prime, C, S. Then I just got confused. And where all these choices come from? And let's say one, like a mysterious part when you read the Kato's paper. So let me just point out what's going on very roughly. So we start with the two Ziegel units. And it is denoted by like a C, G, alpha, beta, or D, G, gamma, delta, whatever. And they lies in some unit of the ring of the open modular curve. With certain level structure. And like by making the pairing of two elements, we get an element in K2 of the open modular curve over Q zeta M for some abelian extension. And here, the pairing comes from the Steinberg symbol in K theory. And there is certain twist, which I will explain at the fourth talk. Especially the Christian S is involved in this twist. And from this, we have the Chern character map. Then we get an element in H2, Y1N over Q zeta M and ZP2. And using the Huxley-Serre spectral sequence, we get a map from H2 to H1, Q zeta M, and the first set tau cohomology of X1 and QR. And X1, Y1, yeah, you don't have to worry about it too much right now. And ZP, yeah, twisted by the square of the cyclotomic character. Yes. And this guy is, of course, H1 et al. X1n. Oh, this one is over cuba now. So it really has the Galo action first. Okay, now I split the Tate twist. And the first one is the Jacobian of this modular curve. And here, there's some twist. To have the correct Galo module. H1 et al. X1 and Q bar ZP1. Of course, this is not, I mean, this twist is not free. So in order to do that, we consider everything over Z mod P and Z and adding all P power level and taking inverse limit. This kind of thing is required. Then here we get the Euler system for this whole Tal converge of modular curve and tensoring like a height 1 prime, the tensoring by the Hecke algebra quotient by height 1 prime corresponding on new form, then we get a Kato's Euler system of a modular form. But we can just go with this guy right now. And taking the dual exponential map, then it goes to a space of modular form. And all the image is called the so-called zeta modular form. Which is more or less like in the case of elliptic curves or modular form of weight 2, zeta modular form can be regarded as a weight 1 Eisenstein series times weight 1 Eisenstein series. Sorry, weight 1 Eisenstein series. And using from this guy Rankin-Selberg method, then you will get the L value formula. Okay, this is the whole like a picture, and indeed there is some hidden thing. When we construct the Ziegel unit, indeed we first consider certain theta function on the universal elliptic curves. The certain functions on universal elliptic curve. And this Ziegel unit is Ziegel units are constructed from this theta function. Also, these Eisenstein series are constructed from these theta functions. Then this one involves a certain d rock. So yeah, so like a whole this process is making connection from the one type of functions. That's the how I understood the the Euler system paper basically. And in the fourth lecture, we'll go into more detail on this slope picture. And although, yeah, we still have 10 minutes, but I did everything I prepared, and let me stop here. Thank you very much.
Thank you, John. Okay, let me
get some questions. Yeah.
Yeah. Any questions from the audience? I can unmute the audience if they want to ask a question directly. Sorry, is there a question? Okay, so if there is no more question, let's thank the speaker again. So he will continue his mini course from from tomorrow. So this is the end of the morning session. So thanks all for attending it. So we'll meet again after the post lunch.